Welcome to Ask and Learn.
All right, for this problem, so we have three processes. The first one is isobaric, so pressure is constant, and then adiabatic, so Q is 0, and then isochoric, so V is constant. So firstly, let's look at the PV diagram just for the convenience of the following calculation. So first process is isobaric, so P is constant, it's a horizontal line. And then it's adiabatic, it'll be like this. And then it's isochoric, just go back. It's vertical line. So this is the state, initial state, 1, 2, 3, and direction is, so here's the direction. All right. So the problems are, so we need to find out the work, heat, and change in internal energy for each processes. Okay, so for process 1 to 2, the work, so the pressure is constant. So by definition, work is PdV. And P is simply nRT over V dV. I'm sorry, we should not use this relation. No, not this one, not this one. Just hold on. This is not the one that I want to use. Right, okay. So the first one is P is constant, so you simply P times delta V equal to P times V2 minus V1, all right? So what is V1? To figure out this V1, we need to utilize the state equation. PV equal to nRT. And so N is given, R is constant, the initial temperature is given, and we also know the initial pressure. So we can figure out V1 to be 0.0021 meters cubed. So first the process is we compress the gas to half of its original volume. So basically V2 is just half of V1. And we plug in the V2. I see here, I write here, V2 equal to half of V1. So we plug in here, and we can finally calculate the work to be negative 187.1 joules. And the heat added to the gas, to figure out the heat, we can calculate the change in internal energy firstly. That's more convenient. So delta U is N times CV times delta T, right? N is given here. CV, because this is nitrogen. Nitrogen is diatomic gas. So CV is five halves of times R. And delta T, so if you look at this equation again, in the first process from 1 to 2, P is constant, and V just becomes half. N is constant, R is constant, so T also becomes half of the original value. So delta T times C2, no, not C, sorry, N times R, this is CV, times, I just write here, half of T1 minus T1, okay? And T1 is 300 Kelvin, so half T1 just 150 Kelvin. So delta U I found is negative 467.6 joules. So Q, the heat, simply equal to work plus delta U, right? And equal to negative 600 54.7 joules. So this is for process 1 to 2. And for the process 2 to 3, because this is adiabatic, that's right here, 2 to 3. So Q is 0. In that case, we know that for the adiabatic process, T times V gamma minus 1 is a constant, right? So we have relation T2 V2 gamma minus 1 equal to T3 V3 gamma minus 1, right? And T2 is simply equal to 150 Kelvin. And V2 is half of V1. V2 is here. And the T3 is the unknown variable. This is gamma. And the V3 is V3 equal to V1, right? V3 equal to V1. So the only unknown variable in this expression is T3. So we can calculate T3 now. So T3 I found is 113.7 Kelvin. This is pretty low. And so delta U is N times CV times delta T. And delta T here is T3 minus T2, okay? Because we are looking at the process 2, 3. So the result for delta U is negative 113.2 joules, all right? So the work, because Q is 0, so the work is simply equal to the opposite of delta U, which is 113.2 joules, all right? And for the process 3-1, right here, there's not much, there's more room for me. So for this process, we know that the V is constant. In that case, the work is 0. So the delta U, as we can see from the state 1 to 2 and 2 to 3, and it finally comes back to the initial state. So basically, the internal energy change is just the opposite to the summation of 1, 2, and 2, 3, which is equal to negative delta U 1, 2 minus delta U 2, 3. 2, 3. Okay. So delta U 1, 2 we found here. Delta U 2, 3 is the one we found here. So just add these two numbers together and make it opposite. So the result is 580.8 joules. And because work is 0, delta U is given here, so it's simply equal to the Q. All right. So that's it.